So welcome back, everybody. Last week we did not have a lecture because we wanted to focus a little bit on coding. Now, the topic today is a topic which often is left out when we discuss quantum computing, because you're just given the feeling that many of these gates are something which just come out of the blue, and then we simply just implement them without any coupling to physical reality. So one of the things which I want to do today is actually to spool back a little bit before we move on next week to a discussion of entropy and classifications of entanglement. So what we are going to do today is more to look at some of the background theory for realization of gates. So this brings us back to some quantum mechanics, which some of you may have seen. But it's actually useful to see that. So I wanted to give you a kind of theoretical background, and then we are going to move back into the 1-qubit and the 2-qubit gates so that you see that there's actually a physical link with all these operations which we are doing and how you can actually realize them physically. The example which we will look at after we've gone through some of the basic theory here. So if we scroll down a little bit, so let me just look a little bit at the structure of the lecture today. So we are going to review some basic quantum mechanics and how you can represent the solution or the time evolution of a state in terms of unitary transformations. And when we've done with that, then hopefully you've seen some of the basic mechanism, which is a kind of, cornerstone if you're looking at time-dependent many-body systems, because these are many-body systems. And then we are going to look at examples of physical processes, which actually means specific platforms in which you can realize qubits. And one of the first very candidates is something which is called nuclear magnetic resonance. So this is something which has been used in medicine for many different types of applications, but you're actually using states in a specific molecule as candidates for making qubits. Then you can apply a magnetic field to the system, and you can then excite the state from a ground state by using the magnetic field, and that gives often rise to a very simple type of Hamiltonian which acts on the system, which is then your magnetic field times a magnetic moment. And that gives us a simple expression in terms of these Pauli gates. So I wanted actually to, to build up this kind of basic intuition for the different physical processes which are behind the applications which we looked at last week, when we then just said that let us implement an X gate, a Pauli X gate, a Pauli Y gate, a Pauli Z gate. And then you may ask, where do they come from? And there is a whole discipline in quantum computing and quantum technologies, which you could simply call building a quantum computer. That means you have to find platforms, that means systems, where you can identify specific states as candidates for computational basis, which again means defining qubit 0, qubit 1, and so on. And this technique with nuclear magnetic resonance, which has also been extremely useful in cancer therapy, is one of the candidate systems. And the Oslo Metropolitan University, they actually bought a 2-qubit and a 3-qubit machine, which is based on this NMR technique, nuclear magnetic resonance. So after we've gone through the kind of basics of the theory here, with the unitary transformations, we are going to dive into a specific application. This is just one of many of the technological platforms which people are working on. And when we're done with that, then we are going to use these transformations, these unitary transformations, and represent them, as we did last week, in terms of gates. So that means that the way we operate on a physical system is represented by these operations, which we then translate into gates, and a collection of gates becomes a circuit. So if you're going to make a calculation or a simulation on a specific physical system with a quantum algorithm, you will rewrite this in terms of a circuit which then consists of specific gates, where at the end you make a measurement. And you do make these measurements many, many times. So this is a kind of basic pipeline. And I wanted to go back to some of the basics here. And I'm going to use the slides in the beginning, so to remind you of some of these topics. And then after we're done with that, we are going to switch back to the whiteboard and look at the explicit realizations of such gates, physical realizations. So the equation which we're actually looking at is normally what we call the time-dependent Schrödinger equation. This is our equation of motion. In this specific case, we are assuming that there is a Hamiltonian which is not time-dependent. That's the first assumption we're making. Later, we will make it time-dependent. Now, what happens then is that this equation here, when we integrate it up, has a formal solution, which is then given by this time-independent Hamiltonian, and it's multiplied if we integrate from a time t0 to a time t. This is the formal way we would write the solution. And the assumption here when we made this integration is that h does not depend on time. Okay? So we're simply just integrating up these equations. It's a first order differential equation. So clearly knowing the eigenvalues of this operator is a topic by itself with its own complications. Now, when you look at this way of solving the equations, you can now make changes to a system where h depends on time, and eventually to another way of solving the equations where the solution here does not depend on time. And these are called pictures. So what you see here is normally called a Schrödinger picture, but then we have something which we call the interaction picture, which is also very interesting for us because we are going to look at systems where we can have a part of the Hamiltonian which does not depend on time, and where ideally we should be able to solve the problem even analytically. So this is often called a non-interacting part. But you could think of having your Hamiltonian which depends on one part which is time independent, and then you apply an external field which could oscillate like a cosine or sine, which is applied to the system for a specific time. And then you're asking yourself, what is the time evolution of this system? And the whole thing is that these operators, which you see here, assuming that h is Hermitian, it means also that this exponential, which you see, is going to be a unitary operator. So what I wanted to do now is actually to go through some of the mathematical properties. And when we're done with that, we are going to dirty our hands and then look at specific types of Hamiltonians. Does that sound okay? So I know that some of you have seen this in one way or the other one, but I just thought of bringing everyone at the same level here. And please feel free to interrupt me if something is unclear. So what we would say then is that this quantity here, this exponential, represents a unitary transformation, which we would typically label as an operator which takes us from a time t0 to time t. And the way you can read this is as a transition operator, which tells you something about the likelihood of going from a time t0 to a final time t. So this is the parallel to this one is solving Newton's equation. The only difference between Newton's equations and Schrödinger's equation is that Newton's equation is deterministic fully. So if you know the initial conditions, then you know what life will look like in the distant future. Quantum mechanically, you also have a determinism, but there's a probabilistic determinism. So essentially, everything we deal with in quantum mechanical systems is expressed in this right-hand side. So this is pretty formal. And the gritty nitty details are actually left to us. And that's where we can spend years in solving that equation, which looks very simple. Okay, so normally what you do then is introduce, and the reason why I bring this up is that we could think of your Hamiltonian consisting of different parts. So sometimes when you do many-body physics or even few body physics, you could think of this H0 as being a non-interacting part. This H0 could be time independent. And in many cases, you're looking after something or some type of operator, which may lead to exact analytical solutions of a part of the problem. And then you would act on the system with some interaction or perturbation. So this H of I stands for an interaction. That piece can be time dependent. It doesn't need to be, okay? So this is very formal what we are setting up here. And in general, these operators, H0 and HI, do not commute. If you're thinking of H0 being something which involves the kinetic energy, that does not commute with the potential energy in general. So what you want to do then, you can use different tricks here, is actually to define a unitary transformation in terms of this H0, which is then known. And sometimes if you have defined a computational basis, that computational basis could be the eigenbasis of H0. That's often this kind of approach you would like to follow. But it's not needed in the description of the formalism here. So that means that we have now defined a new transformation compared to the one which we had previously. So this is again a unitary transformation, and it's carried out at the time t on the wave function in that Schrödinger picture. So when you see this subscript s here, that means that this is the wave function which we had in the Schrödinger picture. So we are just taking, so suppose somebody gives us this solution here, and then we can perform a new unitary transformation, and then bring it into what we would call the interaction picture. And you will see why we call this interaction picture, because this is a picture which is going to depend only on this H of I, which can be time dependent. Now, one reason why I'm saying this is that when you apply an external field, if you think of these magnetic resonances, nuclear magnetic resonance, what you often do then is to rotate the system in the framework of a specific axis. So you could actually perform a rotation, and that could be represented by this operation which you see here. Because often you have a field which is aligned along a specific axis, and your system is precessing around. If you think of a spinning top, precession means that you have something which is tilted with respect to rotation axis, but you could apply a magnetic field to a specific axis, and you would like to transform it into that reference frame. So this operation which you see here could then represent something like that. And we are coming back to that when we look at the practicalities. Okay, does that sound okay? So, and then you would like to apply a time-dependent field, which could then be a magnetic field which oscillates in the X and the Y direction. So you're processing around a set axis, and then you can have oscillations in the X and the Y direction. And these are the type of operations which an experimentalist can apply to a physical system. So when people have been studying these nuclear magnetic resonances, this is exactly what they do. They manipulate the spin state of the systems with magnetic fields. So this brings us actually back to good old-fashioned atomic and molecular physics. And when you bring this kind of formalism down to the gritty-nitty details, you have always to think in terms of a specific platform, a specific type of system, and then the experimentalist has at her or his disposal a specific apparatus. This could be a magnetic field they can manipulate, or they can have lasers. We do quantum optics. That is another type of platform which is used for quantum computing realizations. Okay? So I'm trying to link this with what is going to come now. So this is a kind of a little bit boring repetition of some formalism, which some of you may have seen. You can take the time derivative of this equation. So this is actually Schrödinger's equation. This becomes your equation of motion in this new picture, because you have now rotated the system or performed a unitary transformation. And when you take the time derivative, the basic assumption was this H is time independent. So this could be you having prepared the system in a specific state. This becomes very relevant. So I am anticipating many small things, because when we are going to run a simulation on a quantum computer, we need to prepare the system in a specific state. So your qubits will be in one state in the beginning. And then we want to run a simulation by applying different types of rotations, which are gates. And then hopefully we could be able then, by some magic algorithm, to find, let's say, the eigenstates of the systems, which essentially is what we do in the project number 1. So the preparation of the initial state is actually an extremely delicate thing. And that could be this state here. We are coming back to that. And in project 1, we have a pretty simple system which we can rephrase in terms of 1 qubit and 2 qubit gates. But in principle, you can have many such qubit states which you want to have as an initial state. So you take the time derivative, and that means simply taking the derivative of this equation here. And that gives us this equation which you see here. So I hope you don't get offended if I'm just taking derivatives of pretty straightforward expressions. And with that, you can then reorder it. And if you reorder it, you can actually use the definition of the Schrödinger equation. So you can subtract H0 and add H0. And with this one, what you end up with then is an equation of motion. So this is a new equation where we have defined a new Hamiltonian compared to the previous case. And this H of I, T here, that is a time-dependent quantity, which is then defined in terms of these two unitary operations. So when we are going to look at this explicit case of nuclear magnetic resonances, we're actually going to perform rotations like this, or operations like that. So everything we end up doing is unitary transformations. And these unitary transformations, when you want to realize the systems, they have to be coupled to some kind of physical mechanism which you can implement. And that could be a time-dependent magnetic field, or it could be a laser pulse, which you implement on the system. So what you see here, this equation here, the second line here, that is just your new Schrödinger equation in what we call the interaction picture, where you have simply rotated away a specific part of your Hamiltonian. And this is essentially what you often do when you are looking at these systems, because then you would rotate it into a reference frame, your system processing around an axis, and then you impinge on that system which is rotating around an axis, or processing, as we call it. And then you simply just think of a spinning top if you have forgotten what precession is. Snurrebass from Norwegian. Okay, so this is the operator which we end up with. And then the order operator is actually important, since this H0 and H1 in general do not commute in general. And that means that the expectation value of a given quantity can then be rewritten as, if you're thinking of the expectation value in this Schrödinger picture, where we had H0 and Hi, that can actually now be rewritten where we have now redefined an operator in this new picture. So this is a transformed operator. So as I said, in just a few moments, we will look at specific ways of writing this exponential operation. And clearly, what we get then when we do that is that these two expressions look the same. And that's clear because it's like you having probabilities which are conserved. There is no smart transformation of your probability which makes you a lotto millionaire. Sadly, I'd wish there was something like that. And the same thing happens when you perform a unitary transformation. That doesn't change expectation values. So your energy, irrespective of how you measure it, should be the same in different frames, okay? So these are just kind of quantum mechanical background technicalities, which I just wanted to bring up. Now you can then rewrite, if you take the time derivative of that operator in this interaction picture, so this I for interaction, then you will actually rewrite it like that. And that means that this new equation of motion is now given by this commutator here. This is a technicality, which we will also use later. Now, this unitary operator is a delicate thing. So the different gates which we will be implementing, they represent different types of unitary operations. And there are delicate actually assumptions about how these are implemented. So sometimes we would implement something which we call the adiabatic hypothesis, which means that an interaction is switched gradually on. And then the system adapts to that. And then after some time, this interaction is switched off. And the system, in a sense, returns back. But sometimes you can just have a sudden and hard switching on of an interaction. And then this adiabatic hypothesis, which you will see a little bit later, is something which you cannot use. So there are different types of operations which require some rethinking and some slightly different mathematical formalism. But this operator which you see here is an operator you want to be unitary. And we want it obviously to have a value that when we stay in the same position or same time, it should be equal to 1. And then if we look at these operations, we want this to be unitary. So if I now take the emission conjugate of T of T prime and multiply with that one, this should be the same as taking U times its emission conjugate. That should be equal to 1. We want this to be unitary, definitely. And there is a further property which simply tells us that we can rewrite this operation in terms of the operator going from a time double prime to a time t. And also, we want this to be normalized to 1. So that leads to these important properties. So these are properties of these operations. And that's simply because quantum mechanics is a theory which is based on unitary operations. That means also that we have a reversibility, which is often very difficult to implement in a classical system. Any questions? So I know that many of you have seen this before. So the properties of this operator, if we now look at it, so if we look at the definition of the Schrödinger equation in this interaction picture, you can rewrite it like this. And that means you can rewrite it in terms of this transformation, which you have here, times this operator H with a full operator here. And that defines, when we now look at this one, we can now rewrite it in terms of the wave operator or the wave or the state at a time t0 in this interaction picture. And then we have a set of unitary transformations. And it means that we would then define from this last expression, which you see here, you would simply define that one as your unitary transformation from a time t0 to a time t. So these are, as I said, these are a series of technicalities which we then are going to break down and look at the specific implementations. So I'm going to go a little bit fast through some of them, but it means that we can actually define an equation of motion for the operator itself. And this is something which then leads to us setting up the final expression for this operator. So I'm going to go a little bit quickly through this because it contains some technicalities which are not so important for us, but I've added them for completeness. So if you now look at the equation here, you can actually integrate from a time t0 to a time t, and that means that this operator here, since this one is defined to be 1, then it's simply given by this expression here. That's the, and your operator H of I, is a time-dependent operator. So as I said, this H0 could be a time-independent operator, which has initialized your system. And then you put a perturbation on top of it. And that is given by this operator H of I. Now, this is something which we can integrate up and rewrite in a different way. So I'm going to skip this a little bit because we can actually solve this equation which you see here. This is an integral equation. You can solve that iteratively by starting with a guess and then keep going. So you can actually make an expansion in terms of different powers of this H. And I'm just going to go quickly through this, and I'm going to skip some of this because these are technicalities on changing orders of integration and so on. But the important equation is the one which comes down here, and this is the last line here. So this operator can actually be written. So this is a time order product, which means that you are looking at an exponential where these operations, H here, are now given in terms of an ordering according to time. So at the time t0, you act with the operator. Then at the time t1, you act again. So these times come subsequently. This is called the time ordering operator. Now, this is actually, one of the things you should keep in mind is actually this is final expression, because that gives you also a kind of intuitive understanding why some parts of an external field can be suppressed and not. We are coming back to that. So when you look at many of the applications, the actual applications of, let's say, a magnetic field on a system like that, these fields will oscillate with a specific frequency. Then in the long time limit, when you act on the system, some parts of this can be suppressed. And then you can actually go back to this expression for the unitary operator in terms of the exponential. I will come back to that. So we are going to take a kind of, in some of the details for the final implementations, we will obviously not go fully into it because it requires, let's say, an understanding of quantum optics, magnetic fields, etc. But I just wanted to keep this at a kind of overarching level so that you see where some of these terms come from. There is an alternative in case you want to have a Hamiltonian here, which is time independent. And in that specific case, there's something which is called the Heisenberg picture. And then you would have a transformation, a new unitary transformation where you take the full Hamiltonian and act on your solution in the Schrödinger picture. And since if you combine this with the Schrödinger equation, you actually have the following equation of motion because this psi is going to be time independent. That's just another way to rephrase things. And then an operator then will be given by this unitary transformations. And then you can actually get, by taking the derivative, time derivative, you can get a new equation of motions. And we note that an operator in the Heisenberg picture can be related to the corresponding one in the interaction picture by this transformation which you see here. So these are just different types of manipulations which you can do on operators. And it depends a little bit on the type of problem you have. So this interaction picture is one of the more commonly used because you can think of you switching on an interaction which is time dependent. So if we now look at these different transformations, what you will have is that since the Heisenberg picture has a wave function which is time independent, this corresponds exactly to the solution at the time t0 for the interaction picture and the Schrödinger picture. So that means that you can relate this wave function to that of a given time t via the time evolution operator, which is given by you integrating up to time 0 from a time t. So there are many ways of using either the Heisenberg picture, the Schrödinger picture, or the interaction picture, and that depends a little bit on the type of application you're interested in. So one thing which I will skip here is actually this about adiabatic switching, because that is not so important, but you could think of you acting on a system. So the system is prepared in a given state. And then at a certain time, you switch on the interaction. And this interaction is switched on adiabatically. And you see this in the terms of this epsilon is a small number. And this is something which you then can switch off also slowly. And then the system would then return when you integrate from t minus infinity to plus infinity, then the system will return to this Hamiltonian. So you could think of having this typical hypothesis is very much used when you are applying a time-dependent field, which then acts just on a specific time. And then you're asking yourself, which state is my system in now? Now, this is something we will come back to when we are looking at realizations of entanglement, because this type of adiabatic switching is something which we can use then to bring a system from, let's say, a 0-0 state to a mixture of 0-1 and 1-0. That means an entangled state. So the type of operations you do then is actually very much dependent on how this perturbation looks like. And the one common way to treat it is actually to think of this as something which is switched on slowly, so that the system evolves from a given state governed by this H0 operator. And then after some time, it's switched off and the system returns back to its original state. Okay, any questions so far? So I'm going to skip some of the slides, but the thing I wanted to look at now, so this is not so important, but this is the second part. And one of the, really classic quantum computing platforms, which gives us directly the Pauli matrices and rotations in terms of those, is nuclear magnetic resonance. And this was really one of the first proposed platforms for realizing these type of operations. So it uses the spin state of molecules. So you can think of a molecule like chloroform, which has hydrogen atoms and carbon atoms. Each one of these are different nuclei, but they can have spin 1/2. A hydrogen atom has spin 1/2. Carbon-13 has spin 1/2. So this is a nuclear spin degree of freedom. Now, these different nuclei will have different so-called gyromagnetic factors, which then obviously depend on the system. So that means that each such nuclei, when you apply an external field, will have a hyperfine structure, or this so-called Zeeman states. I don't know if that rings a bell, but that's one of these kind of states you can have in atomic physics, where you can excite the system from one low-lying state to a higher one by applying a magnetic field. And the hydrogen atom will have a different energy spacing between the low-lying state and the next excited state. The carbon atom will have different frequencies as well, differences in energy. And that means that you can think of this hydrogen atom in chloroform and the carbon atom as two different qubit systems. So they're just different atoms, right, in a molecule. And then you can manipulate these frequencies and you can actually make system A could be your hydrogen atom and system B could be your carbon atom. And then you have a 2-qubit system. And then you're picking the states, which are then given by this Zeeman excitation states. I know that not everybody has taken a basic course in quantum physics, but this is a way to relate what you have seen till now with unitary transformation to explicit operations you can do in terms of Pauli X, Y, and Z gates. Yeah?
Is there any difference when you have two different atoms, which of course they have each of their own excited state and not, but then they will also have different energies and stuff. Does that complicate the process?
Exactly. So you have, when you tune your, let's say, lasers or magnetic fields, you have to make sure that these systems can be treated as distinct ones. So you should often find a frequency which matches exactly the excitation frequency of that specific atom. If you have what's called a detuning frequency, which is a difference between internal frequency of that specific system and the one of the applied magnetic fields, then you can risk that you lose this computational basis information which you want to have. So it's a very delicate thing to tune the fields, and the fields, they are not perfectly set up. They will have errors, right? They don't oscillate around just one frequency. there will be some spread in frequencies, which again means that there is a source of errors. So the realization of these systems is technically a big challenge when you want to realize a given platform here. But these have been natural systems which offer themselves as qubit candidates.
But just a quick question.
Yeah.
You have like the carbon atom.
Yeah.
It has like its excited state is 3 times
Yeah.
as high energy as for the hydrogen.
Right.
How would you know that you don't have 3 hydrogens excited instead of
That's a good point. In many of cases you don't know that. So you really have to be careful with the tuning of the frequencies. That's a very good point. And this is what the experimentalists have to live with, right? We as theorists, we can just say this is a rotation gate, right? And who cares, right? So when after this long detour, which we're going to do today, when we go back to the things we are going to implement, life is going to be much simpler. Because we can just think of this as unitary operations, period. If you want to read more, there's actually tons of papers on that. So the way you would set this up, and I'm going to just give you some of the basic things before we switch over to the whiteboard. So you could now think of you having this nucleus, which is then a spin-half system. It doesn't need to be a spin-half system. It could be a spin-3/2 and so on. And the Hamiltonian of a nucleus with the spin, which interacts with a magnetic field, is given in terms of this part here, where we have the spin operator. And this is called the gyromagnetic ratio, which is then something which depends on the specific system you have. So this gyromagnetic factor for, let's say, hydrogen, I think that's something like 42 megahertz over Tesla. If I look at the carbon, this is something like 10.71 megahertz per Tesla. So this is something which is inherent to every specific system. So, yeah. Say it again, yeah. No, that's a vector. These are 2 vectors. So both phase quantities are vectors here.
Yeah. Okay.
But what you would typically do then is that you would orient your magnetic field along the z-axis. And that means that what you end up with then is that this mu is simply your projection. This mu times b would be projections along the z-axis. Yeah. So it's pretty common to actually let this spin interact with a constant magnetic field along the z-axis. And then what you end up with then is that you get an effective Hamiltonian, where there's omega here, which is called the Larmor precession frequency. And this contains specific physical constants. So what I'm doing now is just I'm lumping together the system-specific physical constants in terms of h bar times this frequency. And then we have sigma z here. So if you go back, this S here is actually the spin, this X component is the Pauli X matrix divided by 2 times h bar. So h bar comes from this relating to the Pauli matrices. So then if you think of this one as just an effective type of Hamiltonian, this is what will act on the system. So it includes, there's some typos here, magnetic field along the z-axis. So this quantity here, your field along the z-axis could then just be a constant. So this is time independent, okay? So you can think of applying this as a type of time independent part of the Hamiltonian. So when I then do the transformation here, what I'm going to do, if you now think of so this is going to be a 1-qubit state, okay? Now you can represent any point as a continuous transformation on this block sphere, which we discussed in the second week. And in that case, we could think that at the time t equal to 0, your state is prepared as a linear combination between qubit 0 and qubit 1. And so this could be any point on your sphere. If you put the angle equal to theta to, let's say, 90 degrees, then you would have either the North Pole or the South Pole. As we said, so 1 is meant to represent the South Pole, and 0 is meant to represent the North Pole. So this is just your state, the general state. And this is actually an expression we are going to use when we're going to prepare the system. So it could be prepared as a linear combination, or you could just prepare it as a qubit 0 state. This is often the most common choice when you prepare the system. So if you have 10 qubits, you would prepare all of them in state 0, and then you would have the tensor product over 10 qubits. So if you do that, now we can apply this field. So now you see the time dependence coming in here. So this is back to a unitary transformation, where we now act on the system we have prepared at time t equal to 0. And that means that what we end up with when we apply it is that if we now insert this block sphere ansatz, what we get then is something which looks like this. So we have the unitary transformation acting on the states which we have here. So when you do that, one thing, so we're just going to switch over to the whiteboard. One thing I just wanted to remind you of is something which we discussed 2 weeks ago. So if you have a given rotation operator A acting on a vector space A with eigenvalues A, so we're assuming that these A's are eigenvectors of this A, eigenstates, then you can write this out in terms of simply the exponential of the eigenvalue times this A. And we remember now that if we look back here, so if you look at this A which we have here, in our case, that is just the sigma z operator. And then so that is this operator A times some constants. Okay? And sigma z, when that acts on 0, that has eigenvalue +1, and it projects out 0. When it acts on 1, it has eigenvalue -1, and it projects out 1. So in that specific case, what we get then is simply exp minus here, that's the eigenvalue, instead of plus, times 1 here. So this is our new state at a given time. So what I want to do now is actually to look at some specific implementations of these type of operations on a given state and look at what kind of expectation values we can get. So the question now is that if we take this state here, what is the expectation value of this one for the spin operator in the X direction, in the Y direction, and in the Z direction? So what we will see after the break is that the expectation value along the Z-axis is just a constant. That doesn't change over time, but the expectation value along the X and the Y-axis of spin is going to change with time. And that gives rise to what is called in atomic physics, it's called a Larmor precession. So it will change over time along the X and the Y-axis, whereas it's constant along the Z-axis. Because we also have, it's in a way expected, because we have a constant field along the Z-axis. So and after that, we are going to look at what is called a Rabi oscillation, which some of you may also have heard of, which is another type of application of a magnetic field or electromagnetic field. And then a Rabi oscillation is simply going to be our system oscillating between state 0 and state 1. And this is actually used when we now take 2 qubits and we want to entangle them. Because then a state which could be prepared as a 0-1 and then go to a 1-0 state with a 1 qubit operation, etc. Okay, should we take, yeah?
I mean, if we apply sigma on one.
You mean here?
Yeah.
No, but because you have to remember now that if you look at this expression here, so if this is a Pauli Z matrix, so it has this eigenvalue is -1 when it acts on 1.
Okay.
So it comes only in the exponential.
Okay, sure.
So it keeps the plus here. It's what you may be thinking of is when you take the rewriting of the Pauli X matrix. Yeah, exactly. So I just wanted to remind you of that expression. Okay. So we take a small break, and then after the break, we look at really what these rotations look like. And then we can go back to the X, Y, and Z gates and forget everything which we talked about. Okay, so the before we just switch to the whiteboard, I wanted to recapitulate some of the things which were also discussed during the break. So this way of solving a problem is so linked with an experimental realization. So when you are solving a differential equation, it's very difficult to imagine how you would solve that with an experimental equipment, unless you had this kind of mechanical differential equation solvers, which were the original computers, which were invented in the 80s, in the 1800s, and so on. And then you could actually do a series of mechanical operations and solve differential equations. But now you should think of everything we do here as something which can be realized experimentally. And it's another way of rewriting the solution of Schrödinger's equation, because Schrödinger's equation is something you can solve by many different techniques. You can solve it as a differential equation. You can solve it by matrix inversion techniques, which leads to the theory of Green's functions. You can solve it stochastically, which leads to the whole field of Monte Carlo simulations. You can solve it as a nonlinear equations, which for some of you are familiar with copper cluster theory or Hartree-Fock theory. Or you can diagonalize a matrix and get the eigenvalues. So every one of these different mathematical recipes leads to a method to solve Schrödinger's equation. But some of these are very difficult to think of how you can do it experimentally. So now what you're actually doing is to devise a recipe which can be implemented experimentally. And you can actually follow the system by preparing it in some specific states, and then you operate on it with the external fields or some manipulations of the systems, which you can do in the lab. And that brings you into a new state. And we typically rewrite this in terms of these gates and circuits. So I'm just repeating some of the kind of more overarching things here. Now, what I wanted to do now is actually to take this state we have here, this psi of t, and then just calculate some expectation values. And I just wanted to mention this property of the so-called Larmor precession. So suppose now that you have realized that state, and let's switch to the whiteboard and slow down the pace a little bit. So suppose now that we would like to take this wave function and calculate the expectation value of, and now let me see, why is this one not popping up here? Why isn't that popping up? There it is. There it is. Too many windows open here. So let's look at this state. So we have defined a state now, this psi of t, which is given by this unitary transformation, u of t, acting on the state at a time t0. And what we decided now is that this unitary transformation, this u, is now given in terms of this magnetic field, where we now have an e to the minus, and then we have an plus I of h bar omega multiplied with the Larmor frequency. There is a time, there is a sigma z, and this is divided by 2 here. So h bar divided by 2 times sigma c is actually the spin operator, which we defined earlier. And this is something which, when we look at it, you can find specific states. So you could think of a state in, let's say, hydrogen. So if this is hydrogen, if you look at this chloroform molecule, which we discussed, then this spacing here is something which is on the order of, I think it's something like 42. I had some data here. Yeah, that could be, there's a frequency of something like 490 something megahertz. And then you multiply with h bar, and then you have the spacing in energies. And these are called Zeeman levels. And this state here would then be something which has an energy of h bar times omega divided by 2. And this has an h bar of omega L divided by 2 here. So in chloroform, you would have another case. So this is a spin half. So this is the spin of the atomic nucleus. It's just one proton. And then the other atom which you have in this chloroform molecule is carbon-13, which is another spin 1/2 object. And in that case, I think this frequency is something like 100 megahertz. I don't remember exactly the numbers. But again, this would be something which then would be omega L. And now we're putting a C here to indicate that this is for carbon. So these frequencies are different. And we would have an h bar omega L of, so this is a plus here. So this is spacing between these two states. And in the literature, if you go back to a text in atomic or molecular physics, this is normally called the Zeeman splitting. And each atomic nucleus has its own Zeeman frequency, leading to this Larmor precession. So now one of the things we could do now is to calculate an expectation value of these operators. So we could take sigma x, for instance. And this is the same if we use this physics notation. It's written like this. So that's the same. And in our case, that means that we would have an h bar divided by 2. So this is x times sigma x times h bar divided by 2, which defines as sx. And then we have the state 0, which now is multiplied with this e to the minus I omega L of t divided by 2. And then it has a cosine of theta half. And this is then, so this is that part. And then I have the plus, and then I have the state 1. And this is now a state which has e to the I omega L of t divided by 2. And then I have the term here, which comes from the other angle. And then I have a sine of theta 2 here. So that's this part. And this is then multiplied with the sigma c matrix. So this has to be multiplied with the sigma c, which is 0, 1, 1, 0, like that. And this is again multiplied with the ket side. So that means that I have now to plug in e of I of omega L of t divided by 2, cosine theta 2, multiplied with this one, plus e of minus I omega L of t divided by 2, sine theta 2 of e I phi times 1, like that. And then we remember that 0 and 1 are just given by 1, 0. So this is now just us having to perform the right operations here. And if I do this, so I'm not going through all the intermediate states, so I hope you can forgive me if I don't do all the boring linear algebra here. So it's actually u. We know that when sigma z, so let me just quickly remind you. So this is sigma z here. So sigma c acting on the 0 state. So this is the same as sigma x acting on, sorry, that one, on the state 0. We know that that one gives us, if we take 0, 1, 1, 0, acting on 1, 0, that is simply 0, 1, which is 1. So that means that we just switch from 0 to 1. Okay? So we have to be a little bit careful now when we are calculating these expectation values, because it means that when this one acts on that state, it changes it to 1. And when this acts on this state, it changes it to 0. So when we take the overlaps now, then clearly this one, which has now been changed to 0, has to match this one. And similarly, this one has then to match this one, because that's the only one which will give us a norm 0, 0 and 1, 1. Okay? So if I do that, I end up with a final expression where this expectation value is now given, and then I use trigonometric relations for the sine, the angles. So I get a sine theta, and then I have a cosine, and then I have this angle phi minus omega L of t. If I do the same for sigma y, what I get then is a pretty similar expression, except that now I have a sine theta, and then I have a sine theta again here. And now I have a phi minus omega L of t. And if I take sigma z, this is the same as h bar divided by 2 times cosine theta. So what we see now is that the y component experiences the same oscillation as the x component, except that it's shifted by a phase of pi half. So if you look at the x component, which is this one, and the y component, so there's a cosine and there's a sine, and that gives a rise to a factor in value, which is just given by 90 degrees. So you get the same value if you just shift the angle by 90 degrees. So this means that these two are oscillating between specific values, whereas the z-axis is constant. So if we want to summarize this, so you see now that the y component, that experiences an oscillation, so oscillates as the z component, as the x component, but with a angle difference, but with a pi half phase difference. So what we can see then is that this spin half system, so we took a nucleus with a spin half, that is actually a system which is now precessing around the z-axis. So the z-axis is constant value. So the system is actually precessing, if you just think of a spinning top, around the z-axis. So the way you can think of this, if you want to, or you can actually visualize this, if you want to, it's actually not so difficult. So the whole task when you're dealing with this type of systems is to be able to find states like those which you see here, which then can be used as qubit candidates. So what you could think of now, if you go back to the system, so this could be system A. So you would have 0 of A. This would be state 1 of A. So we can just put labels here. And this state here would be 0 of system B. So carbon 13 is system B. And this is system B as well, the excited state. And then if these are well-separated frequencies, you can actually apply a magnetic field and tune one of them without affecting the other one, and then vice versa. And this is essentially what you do. So when we are doing operations now, we're actually going to tune either one of the systems or the other ones. The other thing which is nice here, which comes naturally out when you use nuclear magnetic resonance or chloroform here, is that you have a candidate system here and a candidate system here for making bits. So your computational basis here would now be these two guys here. So you could actually make a 2-qubit gate by manipulating this system. Or we can make a 1-qubit gate. So when we say a 1-qubit gate, then we are acting on just one of these. So let's now look a little bit at a 1-qubit gate. And one of the standard techniques, which is often used, is this of a radio frequency pulse. So that means that you could now think of replacing your field with something which is time dependent in the X and the Y directions. So a so-called radio frequency pulse, is one of the techniques which are often used. So you could now think of having a field B of t, and I'm not able to boldface it properly, so these are vectors. So in the slides, you will see these as boldface quantities. And this could be something like a constant, which is given by some material-specific constant, which I just call for delta. And then it has a magnetic field along the z-axis. So this is your field. And then you could have some field which has a constant here, RF for radio frequency. And this is multiplied with a cosine of a radio frequency and multiplied with the x-axis. Okay? So the way you could then think of this is you acting with this field on the system. And suppose now that we go back to this block sphere, and we keep this as our y-axis, then we know that when we go 80 degrees up, we have the qubit 0 state, and then we have the qubit 1 state down here. And let me try now to make a sphere here. So the way you can think of this is that you're performing rotations of the system. So now you're making a rotation where you could now be on your block sphere. So this is a given time. And then you keep rotating the system till it then gets down here. And what you're applying is an RF pulse along this direction here, in this specific direction. Now, the state which you have here, if this is your x-axis, this is something you could represent as a linear combination. When you look at this state which we defined, this cosine of theta half times 0 plus e of I phi of sine theta half times 1. And then you would have an angle. So let's see if we can plot the angle. So this would have an angle phi. And then clearly we have the angle here, which is theta. And theta goes from 0 to 180. Phi goes from 0 to 200 and 360. So the state which you would have here could now be along the x-axis. This is given by 0 plus I times 1. And the one which you have on the other end would be with a minus I times 1. So this is the kind of states you can realize on this block sphere. So any point on the sphere is a representation of your state. So initially, you would typically initialize your system into, let's say, 0 or 1s. Now, when you, what is often done then, when you do this type of operations, is that you use something which is called the rotating wave approximation. So I'm just mentioning these names here. So you would often fix this field So I don't want to get too much into all these kind of details, but I wanted to give you a kind of feeling of the kind of expressions which we are ending up with. And in that case, we could have a field which is a plus minus here, depending on time, which contains this constant for the radio frequency. So that's a field-specific constant. And then I have a cosine over WRF times T and multiplied with X. And then there's a plus minus. And then I have a sine of omega RF of T times Y. So what many people typically do then is to transform the system by transforming it into the z-axis. So you have a reference frame where you perform a rotation into the z-axis. So your first operation which you would do then, this t here, is actually to take a transformation into the z-axis. So I'm writing this as an operator, and then this depends on a frequency times t, where you multiply this with psi of t. So this is you transforming the system into a new reference frame. So that's the first operation you would do, because you don't know which is the reference frame, so you have to opt for a reference frame when you're going to make the measurements. So one typical operation you could do then is actually to take and transform this system into a reference rotating at an angular frequency, which is this W radio frequency. And the operator which does that, so this specific operator is actually, so this one is nothing but the exponential of minus I of this frequency, and then I have time multiplied with a sigma z divided by 2. That's the first unitary transformation. That is going to give us an effective Hamiltonian. And then with that effective Hamiltonian, we can actually then set up types of operations. Now, there's a whole series of manipulations which you can make here. But one of the things you often try to do is to find a frequency which leads to a Rabi oscillation, where you oscillate between 0 and 1. So a very typical Hamiltonian, which is often used, so you can actually set up different types of such Hamiltonians, is to approximate this one with minus h bar omega of 2 times a sigma x, sorry. And this is normally what we've been calling an h bar omega. And this frequency is normally called a Rabi frequency for Rabi oscillations. And then we would rewrite this in terms of this operator x. Remember now that we defined sigma x, and you will see that we are going to use that consistently. We write sigma y in terms of a y, and then sigma z in terms of a z here. Now, this is you can do many manipulations here, because you can assume that this specific frequency, this Rabi oscillation frequency, matches the radio frequency. And that will often tune away due to the exponential character of this unitary operator, which we saw before the break. You can then, in long times, you're running the simulations, you can then, depending on the values of this RF, you can then replace everything with a very simple operator here. The same if you look at this one. So this would actually rotate the system into a reference frame, which is governed by the z-axis. In this case here, you would put in a rotation which brings you along the x-axis, and your system will then oscillate between a state 0 and 1 due to this sigma x operator. So there's a lot of more, how to say, set of operations you can make, but it's pretty common then to assume that this Hamiltonian which you're dealing with, which performs the operations on the systems, can then be represented by some of these matrices. Okay? So that's the basic underlying, how to say, link with experiment with all the machinery which we are going to develop. And typically then, when you're looking at an operation like this one, which you see here, you could now think of your system being prepared in a state 0. And then you would write this like this. And this brings the system into a new state. And in our case, this would oscillate between a 0 and 1. So this would actually give you a state 1 when you do that. But physically, you're actually implementing physical processes on the system. So we replace this operation where we now have an Rx, which is given by this E of I of omega, and let's now just call this omega, multiplied with T, multiplied with a sigma x divided by 2. And what we are doing now is that we take this operator Rx and act on that on a specific state. And in our case, this gives us a 1. This is also called a NOT gate. So classically, a NOT gate is you inputting bit 0, and you get out bit 1, or you put in bit 1, and you get bit 0. So this is the quantum mechanical variant of a NOT gate. Okay? And then we can actually do manipulations. So the whole thing is that we can implement these type of operations to get, let's say, a rotation around the x-axis. So if I take, suppose now I take an Rx, and it's pretty easy to see that, so let me write it out. And I do an angle of pi half, and then I take an angle for a rotation along the y-axis with just an angle, let's just call this an angle theta. And then I take Rx and I rotate with an angle pi half. So if I write these operations out, so the Rx with an angle pi half, this gives me a state which looks like 1/2. And then I have the identity matrix. So now I'm actually using these expressions for these operators because it's an angle minus pi half. So what I get then is that this is a minus I times a sigma x. And then this is multiplied with the operation of the sigma y gate. So this is a cosine theta half multiplied with the identity matrix. So now I'm actually going back to one of the exercises you had in the second week, where we were actually using the general expression for the Pauli matrices to write them out in terms of cosines and sines when we have this exponential. And this is then given by minus I times sine, and then I have a theta half multiplied with the sigma y. This gets multiplied with 1 divided by square root of 2, and I have 1 plus I times sigma x. And if you run through these calculations, perform them all here, what you will get then is, and I'm leaving that as a small exercise to you guys, minus, so this is multiplied with the unity matrix, minus I of sine theta divided by 2, multiplied with sigma c. And that is nothing but a rotation around the c-axis. So these kind of operations become important when we now are going to define how we do the measurements. So keep in mind now that when we do the measurements, we would like to have an operation which acts on a computational basis. So if we have chosen the computational basis to be 0 and 1, these are eigenstates of the Pauli Z matrix. So if I then make measurements and I have a Hamiltonian which is given by a Pauli X matrix, I would like to rewrite that in terms of Pauli C matrices. And you see this type of operations here are operations which allow us to transform from one type of gates to another type of gates. So many of these manipulations are often done when we are setting up a circuit, which means a set of gates in order to perform a measurements at the end. So this quantity which you have here is nothing but the RZ of theta. So what I want to do now, although this is a pretty short link with the way these things are realized experimentally, I wanted to go a little bit back and look at some of the definitions we had last week on gates. And we are going to look at how we can rewrite a simple Hamiltonian. So this is directly linked with the first project on us writing a Hamiltonian in terms of Pauli operators. Because at the end, when we perform these experiments, real life experiments, this is all done in terms of these types of rotations. So that means that if we have a complicated Hamiltonian, we would like to rewrite that one in terms of Pauli matrices. And ideally, if the Hamiltonian has some symmetries, which follows the Pauli matrices, that makes life easier. And that Hamiltonian we will look at the end in project 1, the so-called Lipkin Hamiltonian, is a Hamiltonian which we can rewrite in terms of Pauli matrices only, which makes life much easier. So let's take a look at the slides again. have to find my notes here. So if we now just use the rest of the time here on the notes here, and we are going to look also at the Jupyter Notebook. What we are doing now is that we are taking some qubit and we are performing a transformation to a new state. And we typically rewrite that as gates and circuits. And quantum circuits are then, as we discussed also last time, a diagrammatic representation of quantum algorithms. And the horizontal dimension corresponds to time. So you can think of you applying this unitary transformation time by time. And you move typically from the left to the right, which corresponds to forward motion in time. That's a kind of standard way of interpreting these circuits. And in our case, you would typically have sets of qubits which are stacked vertically on the left-hand side. And then the lines are normally called quantum wires. And they extend horizontally to the right from each qubit, representing its state moving forward in time. And these gates are normally applied chronologically. So we have seen now, so this is a general gate, which follows the group SU2, and you can actually rewrite it like this, where you have some additional parameters lambda, so these are different angles. And you can then write a general gate like this, and we have specialized to at least 4, 5, 6 one-qubit gates. So these are gates which act on one qubit. So the qubit we have chosen is a vector of length 2. So these gates operating on the qubits must be matrices of dimensionality 2 times 2. So, and we have seen these poly X, Y, and Z gates, that they represent specific rotations in space and can be linked to physical processes like you applying a magnetic field on our system. And these gates actually, they form a basis for the algebra SU2. And when you exponentiate them, they will give us a basis for SU2, which is a group within which all single qubit gates live, period. And these are the most famous ones. And as I said, this RX gate, that simply switches, alternates between 0 and 1. The RY gate alternates in the same way, but it gives a phase factor. And RC gives us simply back the same state, except that the eigenvalue for the 1 state is -1 instead of +1. So when we often do operations, we want to rewrite the measurement in terms of an action in terms of Z gates. So the thing I wanted to do now, and as I said, you saw also this kind of operations you can do with these different gates. This is something which you can rewrite this, which up to a global phase equal the expression for an arbitrary single qubit gate. So I'm not going to look at 2 qubit gates today. We will bring that back next time when we are going to look at the 4x4 Hamiltonian, which we have in project 1. So let's just wait a little bit that. And the slides here, they contain also a lot of information about these Bell states, which we discussed. But what I want to do, and this is the first baby step in the project. So this is a simple 2x2 Hamiltonian. And in this specific case, you have just this, you could use your computational basis, 0 and 1, as your basis. I mean, as soon as you make this non-diagonal, 0 and 1 will not be, in general, an eigenbasis of H. Okay, but that's our computational basis. And it means that the solution will be a linear combination of these 0 and 1 states. So this is the Hamiltonian matrix. And the way we are going to deal with this in the project is that we will have a part which we often call the non-interacting piece. And these guys here, this H0, has the computational basis as an eigenbasis. So one of the things we normally do now is to rewrite H0 in terms of Pauli Z matrices. And then if you now look at this interaction piece, this is something you could think of rewriting in terms of a Pauli X matrix. So what I wanted to show you, and you will also find an exercise where we do this, is actually us taking this general Hamiltonian and rewrite it in terms of Pauli matrices. That is a typical step which we always do when we want to perform operations on quantum computers. So this specific system then has an eigenbasis, the computational basis, which we have chosen, and that could be these specific states. And then we have some interaction piece here, which we have left undefined. So this is a trick which we next week will also apply to the 4x4 matrix, which is a 2-qubit case. So the standard trick then, as you can see here, we can rewrite this epsilons, which H0, if we define these parameters here in terms of a Pauli Z matrix and just the identity matrix. I don't know if you had time to look at this, but this is actually one of the steps in the project here. And we can then rewrite the interaction piece as a Pauli X piece, because with this redefinitions here, we have, if you have diagonal elements, this becomes a little bit more tricky. If you only have non-diagonal elements for the interaction, then it would just suffice using the Pauli X matrix. But we also have interaction elements along the diagonal piece. And these are V1 and V22. And we redefine these variables, and then we can write this in terms of this new Hamiltonian, which is now given in terms of Pauli X and C matrices. Now, the thing is that now when we make measurements, the Pauli X matrix is no longer an eigenbasis, does not have an eigenbasis, the computational basis we have chosen. So what we would typically do then is to rewrite the Pauli X matrix in terms of a Pauli Z matrix. And we're going back to the program here, but one of the things which we can do, so let me, actually you can rewrite the Pauli X matrix, and this is one of the things I want you to show in the exercises today, is that you can rewrite that one in terms of a Hadamard matrix times a Pauli Z matrix. So that's an important step in the project. So that means that if we go back then and look at the Hamiltonian we want to simulate, is that we can take this Pauli X matrix and rewrite it as a Hadamard times Z times X. And then we can make the measurements in the computational basis. So when we are dealing with this kind of operation, it's a little bit clumsy because we are linking everything we do with a physical process of measurement. And that is done in a specific basis. So it sounds strange because it's much easier when you just diagonalize. Actually, diagonalizing this matrix is a baby case. I mean, you can solve it analytically. I mean, everybody knows how to solve a second order problem. So there is no way this could compete with any classical way of solving it. But realizing this on a quantum computer is actually a pretty fancy thing. So the thing I wanted to say a little bit about before we stop today, and we're going to bring this up next week, because if you now look at the Hamiltonian which you have, we are going to prepare the qubits in state 0. And when I now perform these rotations, I am mixing this state 0 into a superposition of 0 and 1. Because my solution, if you now think of you solving this problem, if you diagonalize this problem, which we have here, the original one, since I have 8, 0, and 1 as my computational basis, I know that my solution is going to be a linear combination of 0 and 1. Does that sound logical? Great. So that since the solution is going to be a linear combination of 0 and 1, what I can do now is, and what I'm doing here is to anticipate an algorithm which is called the variational quantum eigensolver. So I'm going to make an ansatz where I now rotate my initial qubit 0 which is the way I prepare the system, into a linear combination. The only thing is that when you do these linear combinations, you get a general state on the block sphere. But I don't know whether that's the exact one, because when I diagonalize, so let me just bring that up in the on the notes here, so it's a little bit clearer. So that you see exactly what I want to do. Now I have to figure out which screen it was on. Here we are. So if I diagonalize, so I have a computational basis. Which is 0 and 1. Now, when I diagonalize this 2 by 2 matrix, so my solution to that is going to be a linear combination of alpha 0 plus beta times 1. Okay? That's my solution. When I diagonalize it, diagonalization gives me the eigenvectors, which are these coefficients alpha and beta. So what I'm doing now is to start with this system in a state 0. So I'm going to have a system here where I prepare that in state 0. I know that because I would then, if I have a frequency, this, let's say, Larmor frequency, I know then that the system, I can prepare it in the lowest lying state. And then I can apply a field, like a field or unitary transformation in terms of a Pauli X matrix, and then I can make a linear combination. So what I would do then is to perform an Rx with an angle theta, but then I could do a new gate, an Ry, with an angle phi. And then at the end, I'm going to perform a measurement here. So I just mark it like that, and this will give me something. Now, what I've done is to rewrite my Hamiltonian in terms of Pauli X and Pauli Z matrices. So my Hamiltonian now is now given in terms of a constant times the identity matrix, times a new constant times a Pauli Z, times a new constant E times a Pauli X. Now, the Pauli X can be rewritten in terms of a Hadamard. I should put a hat here, times Z times H. So this is my computation which I'm going to run. So that means that somewhere in here, when I'm setting up the system, I need actually now to set up these states here, but I'm also making an ansatz for my physical system. So when I perform an Rx transformation on it, I'm actually getting something like this. But my Rx transformation is now given in terms of an angle theta, and then I have an Ry. That means that these angles, which I've chosen randomly, may not be something which gives us alpha and beta, which you get from diagonalization. So you see now what my recipe for finding the eigenstate is to play around with these angles, theta and phi here, so that I get these parameters, the optimal parameters. So this is where we have the optimization problem. So let's just go back to the, I'm going to do a final thing here. And let me just sneak in 2 more minutes and we are done, because I wanted to show you my Jupyter notebook here for this specific case. So if you scroll down, you will see that roughly what we are going to do now. So we have rewritten the Hamiltonian in terms of these Pauli matrices. And the first case, I'm just setting in parameters and I'm diagonalizing. So this is the eigenvalue I get by a simple diagonalization of a 2 by 2 matrix, period. Okay? Now what I do now is, since I've been listening to this guy here, I was thinking now I can obviously rewrite my Hamiltonian in terms of Pauli X and Y matrices. If I had diagonalized it like that, I should get the same answer, right? It shouldn't change. So this is what I've done here. My Hamiltonian is now this epsilon plus this C times I, the identity, omega c plus omega times x. So this is my Hamiltonian rewritten in terms of poly x and poly y matrices. And if I diagonalize, I should get the same value, which you see here, right? No surprise. It's just a rewrite of my Hamiltonian. Then what I'm doing now is to make this as an ansatz. I know that my states is a linear combination of 0 and 1. This is going to give me a linear combination. So let's do that. I just pick a random angle, okay? So I could now say that, let's do that. So this is my system, this one. And I do my rotation. This is Rx and Ry. And I'm going to just pick random values for these angles. I have no idea what they are. And you can see here now, I just picked a value, which is pi half and 0.2 times pi. And then I set up my basis states. This is the 1, 0, the 0, 1. The new basis is just the product of these operations. So at time t0, I perform a x rotation, time t1, a y rotation. And now I have a new basis, which is a linear combination of 0 and 1. And ideally, that is something which looks like my solution of the diagonalization, but I don't have the coefficients. Now, if I do this, as you can see here, if I run this case, you can see now that I'm getting an imaginary part of the eigenvalue. So my energy is actually the new basis. So I'm calculating an expectation value because it's not the exact solution, times the Hamiltonian, times the new basis. So this is just the quantum mechanical expectation value. And when I print that, you see that this is not exactly equal to 0.98 by obvious reasons. So what I could do now is just to pick 20 angles. So I'm doing this in a very brute force way, right? And I say, okay, let me just run with 20 angles. I do rotations in Rx and Ry, as you can see. And then I just pick the one which has the smallest difference with my exact solution, because you see I know the exact solution, and I just calculate these expectation values here with a new basis, where I've just done a random rotation. And you can see here that I'm actually picking random values between 0 and 180. It's not very fancy, okay? But you see now where this is going to move. So I can now set up an optimization in terms of the angles theta and phi. And then I can drive the gradient of the energy to 0 as a function of these angles. This is the variational quantum eigensolver, the algorithm which we will implement in project number 1. So I want to give you this kind of top-down view, but you see the basics, right? You take a Hamiltonian, you rewrite it in terms of Pauli matrices, and then you need an ansatz for the state, which is just this qubit, a random position on the Bloch sphere, which then represents a superposition. And then when you have this superposition, you try to find the optimal angles, which give a gradient which is equal to 0. So we will also need the gradients of the Hamiltonian as a function of these angles. These are things, technicalities, which we will discuss not next week, but the week thereafter. So next week, we are going to discuss a little bit about how we can look at a 2-qubit case, but we're also going to discuss how to measure entanglement for a 2-qubit case, which means that we are going to take a small detour into a discussion of entropy. And when we have that, we are going back to the 2-qubit case and try a similar strategy like this, which is going to be a brute force, and it's going to not be very attractive. And when we have banged our head against this less attractive path, we are going to introduce the variational quantum eigensolver, which is a standard way of actually solving these problems on a quantum computer. So if you have time and you want to discuss the project, I mean, feel free to do that. If you have other things you need to do, I don't get offended if you're not here. Okay, I'm going to stop the recording now.